All right, so we're starting recording, and welcome everyone to both my new whiteboard or my new blackboard here, and also to lecture 10. Um, and this is marking the start of the new section. We are just before the halfway of the course, and actually, in some sense, because of partly because me overrunning a little bit in past few lectures, and also um, we deferred some of the topics to the end, or we might not even cover it at the end. We have actually one lecture ahead of a normal class. Usually, it'll it will take maybe one more lecture until you finish thermodynamics in the normal 3B class. So it is a little bit cramped with both the actually just the nature of 3B it is. So I know everyone just had a test and it's probably very stressful. So you're just sort of winding down from that. That is completely understandable. It is part of nature. 3B is a very intense course, even as I mentioned in the lecture one, even in normal session, in normal quarter, and summer session is just making it even worse. However, hopefully you guys are sticking in. On the bright side, there are some topics we will cover in less detail than a normal session. And it is really my goal, just to reiterate from lecture one, my philosophy and my goal that we're teaching you the fundamentals of the idea of teaching you how to fish kind of idea of learning the skills of how to think like a physicist, how to take a problem and analyze it, and also what are the implications of physics, how does it relate to the real world, and what are some of the new ideas we learn to our lives. And those, I think, are the more important soft skills that, let's say, I don't cover every single topic that might show up in whatever stupid MCAT exam will come up. But the point is, once you understand this, because there's no way anyone will teach you everything you need to know in life. So hopefully once you know the soft skills, the way that to think, and sometimes I might talk a little bit more in lectures. It seems like I'm spiraling onto drawing on different applications or looking at different things, but that's hopefully showing you just by demonstration, not by hardcore testing you this, but just by demonstrating how we think, you learn something from that. So hopefully that is the takeaway so far. And I also want to continuously apologize for the overrun, because some of you reflected to me, and I really, really appreciate the feedback. I really want to apologize for that overrun, and I will promise you I will continue to do my best to be on time. This monologue here probably doesn't help, but I want to address that first before we start as well. And I know that even though it is recorded and you can look back, it probably caused a lot of inconvenience. So I just want to publicly apologize for that in advance. We will, however, end a little bit earlier if things goes on plan, on track like this, because I'm making the decision between should I split some of the topic in half or should I keep the recording, especially nowadays when things are recorded with technology. It seemed like in my mind a good idea to have it as each lecture self-consistent, so we actually complete the topic of thermodynamics instead of leaking to another 15 minutes of today and use some. So with that logic, we probably will end, the current syllabus end at lecture 17. And then we'll probably use lecture 18 to fill in one of the advanced topics, as I call it. So that will normally be covered in detail as well in a normal 3B course, but I will probably choose to just cover it in limited detail, give you the ideas, and not heavily examine, put it in the final exam as well. It's a little bit easier on you guys, at the same time giving you all the sort of tools to think and learn, all the soft skills that I was talking about. So that is the goal, but that is not any excuse or justification of, because some of you will have plans after this. And I'm sorry for cutting into that. So if possible, I will see if you can plan for the lectures that might overrun for another 10 minutes past 8. So maybe plan your schedule so that it might go until 8:40. I promise I won't abuse that, and I'll try my best to keep it under as well. So if you can plan the extra 10 minutes of buffer, then if I end on time, then that's great. Then you can I can answer your questions or whatever. Okay. All right, good. Thank you. I agree with the buffer lectures is a good idea as well because physics is one of those things it takes time to practice. So do a lot of practice to do well in exams, as you probably realize in the test. So the more time between review and practice and final, at least those are the best courses I find when I was studying physics. Okay, without further ado, we will start here. So now we will begin chapter 10, which is electric forces and electric fields. Okay. And on the goal of sort of improving ourselves a little bit every day and improving that 1% every time, another thing I will try to do, this is a good point since we're starting a new segment of the class, to change the style a little bit. So normally for lectures, sometimes there's two goals. One is to convey all the ideas I need to convey, and the second is to write down comprehensively all the things you need to know. And in the past, in normal teaching, in live in-person teaching, I'm able to do both within the time frame that is given, usually decently. But now I realized all the little things, as you understand, it takes a little bit longer. Just that extra 5 seconds for every move I do does add up. So I need to make a choice. Should I talk about interesting things less, or should I write down a very comprehensive list of things you need to know, or should I prioritize the former? And my notes would be a little bit more less of a comprehensive list. So I'm going to lean towards the second option because in my opinion, there is no point of, normally there is a point when you deliver a lecture, the students need to copy down everything you need to know, because sometimes you can't absorb everything I say in the real time, right? So they rely on the written words as well. But now the lectures are recorded. So if you look at the notes and something is incomprehensible, you have two jobs. One is you should read the book, and that is always the main thing. As I told you, the content is from the textbook, it's from your reading, it's from your learning. The lectures to assist you with that, right? So so if I just rewrite everything you need to know from the textbook, that's a little bit redundant. And secondly, but usually lecturers still do that, but for the second point is now this is recorded. So even if I start just sketching fancy diagrams and I talk right away, you should still take your notes. So at the end, when I just upload the slides, it might not be as readable as like a story as it should be. But it will, if I start talking about charges today, as you will see, right, I was just drawing this instead of writing down everything I say. So if you look back at my notes, it probably won't be as comprehensible. But so as you take notes yourself while I'm delivering the lecture, you should add little things I say, but I know because I talk fast as well, if you miss anything, there's the recording. So there's the benefit, and that's why I'm going to give you a little warning, give you a little heads up that I'm going to switch the style up a little bit. Hopefully that will help with my timing as well, with a little bit more efficient that way, okay? Okay, so this is actually part of part 3. And I know I called it electricity in the syllabus, but I think I'm going to change it to electrostatic. It's the more formal term. It's like thermodynamics and electrostatic, because electrostatic means that it is when things are stationary. Most of the time, we're looking at the electric forces when things don't move, at least when they don't move a lot. Okay, and then the next chapter is circuits, which is when now we're talking about wires and electrons flowing through electric circuits. Now things will start moving, and especially in the last part about magnetism as well. So is there a lag? Interesting. Okay. We'll see. If it goes really bad, just keep letting me know in the chat. We'll see if we switch halfway. So the electricity, so just to give you the right terminologies, electricity is really, really a very vague term. And most of the times when people say electricity, probably a technical person would think of electric circuits, right? So we'll be a little bit more precise, and I will call this segment electrostatics. Okay, so that's the first word to introduce. Okay, and right up front, I want to introduce a bunch of terminologies that I won't, so that will actually last for the next couple of lectures, that you'll see these terminologies. And a lot of them sound very similar. And this is one source of confusion for students when they learn about electrostatics, okay? And so I want to, right in the first lecture, tell you that all these things are different. And one confusion is students would think that they're the same. Let me write it out and you'll see how similar they sound, but yet they have different definitions. So the first one is electric force. And then there's the concept of electric field. There's electric field strength. And then there's electric field lines. And then there's electric field vectors. Okay, so right off, the other than electric force is its own thing, that's good. But now you see electric field strength, electric field lines, and electric field vectors. They sound all similar, but they're different things. So make sure you learn the definitions of them separately as we go. Okay, so I just want to address that these are different things. When we say electric field, technically it could be any of these, okay? I actually see the lag is very slow. What do you guys think? Should I switch back to a wire connection? Who votes switching back? Okay, good. So I apologize. This is what happened when I tested as well. It seems like Zoom is just catching up with it. Okay, so you'll see a little bit more control panels, but I think it should be faster. Yeah, hopefully. All right. Okay. And then after electric field, these terms that sounds very similar, okay? So when we say electric field, it could mean either of these. Actually, when we say electric field, usually we by default means electric field vectors, okay? But these are different ideas we'll address. And another one, another few is electric potentials, electric potential difference, and electric potential energy. See how similar they sound? You're welcome, Isabella. Especially electric potential and potential energy. So right off today, I want to make you put a star in your notes or something to remind yourself, electric potential and potential energy is different things, okay? I've mentioned this term a few times already in thermal physics, right? When we talk about different types of energy, and now we will actually get to study it in depth. Today, we'll address this side of the column, and tomorrow we'll address this side of the column. So just to emphasize the difference is, one, we use the symbol V, one we use the symbol U. They are completely different things. They have different SI units. Even the units are different, okay? So they're different concepts. So make sure you put a small star and remind yourself just the word of energy is different, right? We'll address that tomorrow. Electric potential difference is not surprising. It's a difference, it's a delta V, okay? And electric field vectors is given by E with a little arrow on top. Electric field strength is just given by E, like that. Okay, electric field lines are lines. They don't have a variable for it. And electric field itself, usually we actually mean electric field vector when we say electric field, okay? So electric field is sort of the general term for this. Okay, so we're going to address that. Now, since we're learning a new topic, right? You want to ask yourself those three questions. So let's reiterate. What are the questions you want to ask? You need to first ask, what is it? What does it do? So what is electric field? Or what is electric force? What does it do? And what? And why do we care? Right? Remember these qualitative questions. It's not only for physics, but when you learn anything new, I would suggest asking these questions. So and now, I think the first thing let's do is let me answer actually the last one. before we go into technical details of what does the force do, and what are the definitions like this. Why do we care about it? Why is why at this point, I mean, sure, it's in the MCAT or in some exams that you need to take. But other than that, if you're learning physics, who cares about electric field? Why is it important? Well, I'll give you two reasons why we should care. The first reason is electric field is strong, okay? Put a double underline on. It is actually an extremely strong type of force. The only other non-contact force that you know so far is gravity. So which one is stronger, do you think? Well, I kind of give it away that electric field is strong. Maybe I should ask, which one do you think, how much stronger do you think it is? Try pop it in the chat while I write down the second point. How many times stronger? I'm not making this very quantitative, but just so throw out a rough number. Do you think it's 100 times stronger, 1,000 times, 10 to the power, let's put a 10 to the power something, 10 to the power of 2, 10 to the power of 3, 10 to the power of 10, 10 to the power of something. Put it down. And the second point is electric forces or electric fields and electric forces are everywhere. Okay. At least one. That's a very safe bet. It is at least one, yes. The answer is, it is, compared to gravitational force, it is 10 to the 40 times larger or stronger. Right. This is a not very quantitative, but a rough number. But imagine writing 1 followed by 40 zeros. That is how much, that's how crazy. That's an appropriate reaction in the chat. Just to demonstrate that, now I'm a theoretical physicist, so I don't do a lot of experiments because every time I try experiments, they fail. That's why some of us go into theoretical physics. Just to show you, I have this piece of little tissue paper and a plastic ruler, and all I have to do is scratch it really hard, and probably by doing that I will rub off, you know, a couple of dozens of electrons. And now I can take this piece of paper, put it over here, and it will completely stick over here for at least a few seconds. It would have longer, but it is a little bit humid in my house today, and as you know, humidity or water conducts electricity, and that makes the whatever electrons I remove from the plastic get replenished by the moisture in the air. But normally that little piece of paper will, on a more drier condition, can stick perfectly on any plastics. So that's why I go into theoretical physics, by the way. Now, you might think that, well, I know that I've played with that since I was a kid. That's called electrostatics, right? Or sorry, that static electricity, right? So yes, but you may not have appreciated this is, let me draw this out, is what am I competing against? If you draw a free body diagram on that little piece of paper, part of it, so I've removed a few electrons, so it is negatively charged. Now it's attracting the positive charges inside the tissue paper. So the electric force is holding it up, but what else is acting on the force? I'm not touching it in any other way. The only other force is gravity that you know. So what is pulling the paper down? It's actually the whole Earth. So I'm standing here holding that ruler with a piece of paper over here, right? So if I draw a free body diagram here, by the way, in this chapter, you'll see the return of free body diagrams. So the bad news is you'll see a lot of free body diagrams again. But the good news is you'll see a lot of free body diagrams, because if you master them, if you still find them shaky, this is the point where you really want to brush up yourself. But once you do, this chapter is going to be very straightforward. So I highly encourage you to do that, right? So we'll draw, remember it starts from the center of mass of everything. So there's this electric force that points up. Normally, you see, I don't like, just a problem solving tip for you as well. I try to avoid fancy subscripts. I think subscripts are just a way for professional people to confuse others. So I try to avoid them as possible, to make things as simple, as intuitive as possible. But I have no choice with the electric force, because if I just write E for electric force, E stands for electric field in a second, at the second half of today. So I kind of no choice over here. So just for symmetry, I'll write down the force of gravity as well, right? So that is usually just called W, the weight, or just G, you know, gravity, or whatever you like. So that's what's competing, and these have to balance. Now, this is, remember, whenever you write down force, speaking of mastering free body diagrams, so every time you see a force, you might want to change your pen color and put a note over here. You should write down what is it on and what is it by, right? And in this case, this is on the tissue paper by the ruler. And in the other case, it's on the tissue paper by the what? By the earth. You have the whole great earth pulling on this paper, and yet just merely just by me just erasing a few electrons from the ruler, I can hold this up. Now you hopefully can appreciate why that little childhood experiment is significant, right? There's this whole mountain, if you think about it, all the, you know, it's not just the earth, right? There's, you know, Mount Everest on this side of the earth that is pulling it down. There is the whole Pacific Ocean, that whole bulk of water that is pulling it down. There is, you know, there is all the people, you know, there's, who else? Donald Trump, you know, sitting in his White House or his golf course or whatever he is, pulling that down. All of these are competing with the tissue paper, trying to pull it down. Yet the little bits of just having that little bit of electric difference between the ruler and the tissue paper was able to hold it up. So that is the power of it, right? And now, how about the second point? It's everywhere. So let's recall ourselves, there is that 4 fundamental forces in physics. We talked about, right, there's gravity, there is electromagnetism, for now I'll group them together, although I haven't justified them. And then does anyone recall the other two forces? They are just, with our brilliant naming creativity in physics, it's just called the strong force and the weak force, right? If you want to be more specific, the strong nuclear force and the weak nuclear force. These are the 4 fundamental forces in nature. These are all non-contact forces. Okay, if you want to make a note, right? Non-contact. Now we're looking at this. Now, before we start this subject, if all you know is your daily experience and physics 3A, before you come in physics 3B, you might think that gravity is probably the most important out of these, right? Out of these 4, what do you use every day? Sure, we look at our light bulbs, especially in the modern age, where you look at your iPhone, your computer, everything runs on electricity, you'll go like, sure. But gravity is not only bounded on Earth, it's also, you know, in the solar system, in the cosmos, with bounding how all the stars and galaxies, how the universe operates. So you might think that is very important, but I'll try to convince you that the electric force or electromagnetic force is very important. First of all, sure, gravity governs all the planets and stuff, but what are they made of? They're made of atoms. Everything in the universe made of atoms. And what is inside an atom? We have a proton and an electron. And what is the force holding them together so they don't just flow apart? That is the electric force. Right? So the electric force is everywhere because everything is made of that. Now you might go, sure, okay, so if I zoom in there, that is fine. But just to show you more is if I have different atoms, we talked about this in thermophysics already, so that's why this is a good next topic to talk about, leading on those concepts of the different types of energy or forces, is there's intermolecular force. And intermolecular force is basically electric force. Okay, so number 1, it holds the atom together. Number 2, it holds atoms and atoms together like that, okay? So I apologize for everyone having to fill in my shorthands, but I tried to have these a little bit more efficient. Hopefully that's okay. So these molecules are held by essentially electrostatic forces or electric forces, okay? at first, you might look at them and see, oh, well, this is neutral, right? Plus and minus, they cancel out. A proton and an electron, they cancel out. So if neutral and neutral, how do they attract each other? Well, because they're not perfectly symmetrical. So they're called a dipole. Di means two, pole, right? Two poles, two ends. So so they're sort of skewed. So on the one side, there's a little bit more negative, and the other side is more positive. So the little bit more positive side, maybe I should have drawn the dotted lines here, would attract a little bit more negative side of things. So they will rotate themselves, you know, they'll rotate themselves in this way, so that all the molecules would, so sometimes we call this leaking out. There's a leakage of the electric force leaking out, or the residue electric force going out. That is basically intermolecular force. That's what that is. So physicists sometimes like to joke that all of chemistry is basically physics, if you understand what electric force is. Okay. I see there is a little bit of lag. Let me see if I can remedy that by turning. Okay, can people still hear me? Okay, good, all right. Just turning off the Wi-Fi and using the landline, hopefully it's a little bit more stable, and we'll see it. Okay, we'll see if it's better. Okay, all right, yeah, so intermolecular force, and now, but then it goes even further than that. Now you have a whole object of molecules, right, made of atoms and molecules like this. Have you ever wondered, first of all, how many of you know that everything you touch, even yourself, your own body, is 99.99% made of vacuum? If you think about it, the nucleus is a very small part that is solid, and then you have a huge gap. There's actually 10 to the 5 times the size between the nucleus and the electron. So if I put if the whole Earth is an atom, if the whole Earth is the size of an atom, then what is the size of a nucleus? The size of a nucleus is not larger than a bus station on Earth. That is the ratio of it. So the nucleus, that is the part that is solid, and then you have all these empty space out 10 to the 5 times of the empty space until you hit another solid object, which is the electron. Everything else is vacuum. That's what we are made of. We're 99.999, at least 4 nines vacuum. In that case, if we are so if I put 2 hands over here and I move my hands together, why do they meet? Why do they not just completely pass through each other? For that matter, have you ever wondered this? How do you even stand on the ground? Why don't we just get sucked completely through the earth, to the center of the earth? How do we even manage to stand on solid ground? If everything is made of vacuum, they should just directly pass through. What are the chances of a nucleus hitting on another nucleus and was balancing there? The answer to that is electric force, believe it or not. So what happens is, the atom is in the middle, the electrons are usually on the outside, the nucleus, protons are in the middle, right? Then all the electrons are on the outside. So on the outside of any object, it's basically filled with electrons. The positive part is, the nucleus is probably more inside, and same as the ground, right? On the top is this sea of electrons where the nucleus is hiding further down. And if I zoom in over here, you'll see what happens, right? Because now you have negative and negative, and they repel each other. And they repel each other. And it is precisely this repulsion that is keeping your feet on the ground and doesn't sink right through to the center of the earth. All right. So now that you're sitting on your chair watching this lecture, the reason your bottom does not sink right through the chair is because of electric force. Tonight, when you go to sleep, the reason you don't just sink right through and dissolve through your bed, that you can sleep comfortably on your bed, is because of electric force, right? The fact that you can pick up your food, you can clap your hands, you can punch each other. It's all because of electric force. And think about just going back to the strongness of electric force. If you are standing on a tall building and you decide to jump off the cliff, I don't know why physicists keep liking this example, but if you do that, the moment you hit the ground, with that amount, all the momentum of there, your comfort aside, you will not be able to penetrate through the ground, right? You'll still stay there, and that is the electric force hitting against the gravitational force, and that is how strong it is, and that is how prevalent where everything is. Okay, so in these lectures, in the textbook, I encourage you to read a few introduction chapters about the history of how people even figure out there are charges. How did people figure out there's two types of charges? I'm just going to drop down a few notes over here so that I'm not doing a reproduction of the textbook word for word. But these are a couple facts about electric charges. Okay, so there's two types. There's positive and negative, and then positive and positive will repel, negative and negative will repel, positive and negative will attract. All of them have a very nice story behind them, and scientists figuring this out. So I'll encourage you to read that. Those are not directly examinable, so if you like, you can do that at the end, but probably if you delay it, probably towards the end, you're more concerned with the exam. So while you have time, it might be a good time to brush that up, but if you don't want to, I completely respect that as well. But that gives you the background of how they discover some of the basic facts. For now, I will just mention a few, two important rules that we need to know is, also, when we learn something new, you want to learn the SI units. And so, sorry, you first want to learn the symbol and then the SI units, right? So what is the symbol for electric charge? The symbol is actually Q. All right, so now you're going to be confused because Q, we just used it for heat. That's why I would encourage you to use delta Q for heat, because heat is always a transfer, so you don't get confused. But normally there's no overlap between these chapters, or very little overlap, so that is not a big deal. Or sometimes we use little q, whatever works, okay? It doesn't matter. If we have more than one charge, we can start putting labels on things as well. So that is the symbol we use, and the SI base unit is coulombs. Okay, so C. Okay. Incidentally, an electron has a charge of negative, because it's minus, right? 1.66 times 10 to the minus 19 coulombs. So it's a very minute. 1 coulomb is quite a large charge. In fact, if you have 1 coulomb of charge, it is actually very, very strong. You don't really want to be near that. You will probably get ionized. So that is it. And this is a constant that comes up a lot because almost everything is made out of this unit. So we give it a name confusingly, just E, right? So just like G equals to 9.81 in terms of SI units, I'm not gonna write that down. E without the hyphen is just this number. So E itself is positive 1.66 times 10 to the minus 19 coulombs, right? So if you like, the charge of an electron, maybe I should write it this way, is minus E. And the charge of a proton is positive E, okay? If that makes sense. Now, this is actually another big mystery in physics, that, you know, the electron is its own thing, the proton is its own thing. Why are their charges exactly equal and opposite? Here's another question that you might not know, that you might not realize that you need to know in your life. Why are they equal and opposite? In fact, if you're asking that, you just asked a great question. No one knows. This is one of the forefront of theoretical physics research. People are trying to realize when things are it is very rare in the universe, things are a coincidence. You know, a coincidence to this great degree, 2 different particles have exactly the equal magnitude of charge, just opposite signs, there must be some reason behind that. And it bugs the hell out of us that we don't know why. This is one of the, if you heard of grand unified theories, string theory, they have trying to solve these problems of this, okay? I realize there's another thing I can talk about more about how electric force is important, but I'll leave that to the end. So that just we can move on to the, it's interesting, but I'll leave it to the end with the key concepts. So the first concept is net charge. So net charge, when we talk about that, right, is the total positive charge in something minus the total negative charge in something. So make sure you understand this concept, that when we say the net charge is 0, it does not imply, right, remember this arrow means imply, it does not imply there's no charge in an object. In the object. We're going to look at conductors where I'll say, okay, the net charge is 0, so it's a neutral thing. And then I will start telling you if I put a magnet or if I put a lot of positive charge here, suddenly this conductor will start to split up, right? All the negative charges will go to one side because it will attract, so this is some external source. And then all the positive charge will get repelled to the other side. And then you might get confused, where does this come from? Where does all this, I thought you said it's neutral. No, it just says that when I say the net charge is 0, there's just as much minus as much positive. So you might ask, so how many are there really? There's two answers. The one is the classical answer and the one is the modern answer. The modern answer is it's not very complicated, a little bit more complicated that you don't have to worry about in this chapter. The modern answer is you count the number of electrons. It's not as bad as it seems because you just have to weigh the object and then you know the molar mass, you can calculate how many atoms there are and then you can calculate exactly how many negative charges and how many positive charges are inside a conductor. However, for our case, we just need the classical answer before even people know about electrons exist, and it makes your life easy, right? So that's why physics is also easy, at least when you're a beginner learning this. All the concepts are pretty, we're trying to make it as easy as possible. The classical answer is there is infinite negative charges and infinite positive charges because people did not even know about things are made of atoms. So they just assume when I say the net charge of something is 0, technically there is infinite, they're making a continuous limit. Sometimes this is called the continuous limit. And doesn't worry that there is discrete charges, but that it's just continuous. So as soon as I bring an external charge like this next to it, it will split up all the charges. So the concept is if the external charge is, for example, positive 10 coulombs, how much negative charges over here will you get? You'll get negative 10 amount of negative 10 coulombs immediately swinging to one side, and you will get positive 10 coulombs immediately get repelled to the other side, right? So the net is still 0. So here's an exercise for you. Yes, the pink doesn't show up as well when you use a new screen. So here's an exercise for you. What if I bring an external charge? So I have a conductor over here. It can be circle, it can be a cube, it doesn't matter. This time the net charge is 5 coulombs. And I'm going to put a bunch of negative charge here. Let's say I put negative 10 coulombs over here. So obviously a lot of positive charges would get attracted to one side of this conductor and a lot of negative charge would get repelled over here. So my question to you is how much of each? So here, Q left equals to, so Q left equals to how many coulombs? And on the right-hand side, Q right equals to how many coulombs? Okay, you can put that on Piazza and we'll address that. Okay, so there's two fundamental laws you need to know that charges satisfy. Number one is that is what I mentioned here already, that like charges repel and unlike charges or opposite charges attract. And the second idea is the conservation of charge. So key idea number one, key idea number two. It's the conservation of charge. It's a new law, like conservation of energy, or something like that, right? What do we call it? What do we mean by laws? It's things that we cannot prove, okay? So any theories Because physics, by the way, is one of the rare subjects where you can keep asking why, and there's always an answer. So one thing that, no offense to any chemistry or chemist, is that one negative experience I had even at a very early age, I think in high school, when I asked a chemistry teacher when they were teaching something, and I asked, why does this happen? Why does a certain reaction happen this way and not the other way? I think that was something like that. And the answer I got was discouraging. This is just the way it is. You just have to memorize it. And that was a big turn off. And then I realized in physics is the answer is actually in physics. That's why they don't know the answer. Probably no, it's probably beyond my level back then. But the point is, in physics, the idea is we want to keep asking why, and there's always a reason why. But you understand that when you keep asking why, you have one reason to support another, and you go down the rabbit hole. There's always an origin. There must be some assumptions you need to start with. And those assumptions are what we call laws. At least at that point in history, that was not able to be explained. Okay, so conservation of charge and why they repel and why the opposite charges attract for ages. Actually, it's only the past 40 years, once we have a deep understanding of quantum field theory, that we have the reasons why that charges are conserved. In fact, we now know why energy is conserved, which was a long time called just a law of conservation of energy, right? That's what theoretical physics is about, if anyone's wondering. So these are what laws are. So just to give you an idea, when you hear physicists talk about laws, now you have a clearer idea what we are talking about, okay? So speaking about laws, this is a nice segue in, let's introduce another key laws about the electric force. It's called Coulomb's law. Right? So now that we know that fact, if something repels and something attracts, we want to ask, what is the magnitude of it? Now let's dig deeper into the actual numbers, the quantitative part, not just the qualitative part, right? So after you understand the qualitative idea, we will introduce the Coulomb's law. What it does is, you want to make a note, it gives you the magnitude of the electric force. Okay, so we talked about electric force is strong, electric force is everywhere. Now let's calculate that electric force. So that's what I mean. You can use a lot of symbols. You can use any symbol you like. You can just use Fe for now. The first time I'm introducing this, I'm going to make it more explicit. It's given by K Q1 Q2 over R squared. I'm going to put a magnitude on here, which you sometimes don't see in books because, again, they assume it's understood. So make sure you understand it's there before you drop it, okay? Now, there is a vector version of it. So there is a vector version. However, lucky for you guys is you are first learners, you are beginners in the subject. And you, even though this is presented in the textbook, this time without the absolute value sign, as you can see, you don't have to worry about this scary vector hat thing. Now, if you do write things in vector, make sure if one side is a vector, the other side also has a vector sign, okay? So you see a symmetry over here, that if one side has a hat on top, the other side has some sort of hat on top. You cannot never write something like this. This is wrong, okay? You need to have some symmetry, okay? So my advice is, although the textbooks will probably sometimes would introduce this and say that you can do problems this way, and yes, of course they're right, you can do it using the vector version. It's much easier to do the magnitude. So this version gives you the magnitude and the direction separately. Okay, so this is the problem solving tip over here. Now let's define all the variables. This is a charge of everything. I'm not going to write them down, but in an exam you need to. But I'm going to write down the two less obvious ones. One is the R, which is the distance between the center of charge. So if you have this charge Q1, Q2, should I measure the distance from the edge of this or from the short edge or from the long edge? Neither, right? So you measure from the center of one with the center of another, like that. That is the R that you should go. So you might want to underline center of the charges that way, okay? As a result, a lot of the times we will use the term point charge. we'll just approximate everything as a point. Turns out the electric force on a spherical charge, acts exactly. So if I want to know the charge on an electron due to this sphere compared to a point charge with the same charge on the electron, they have the exact same effect, right? Let's say this is positive, right? Let's say this is plus Q. So if I draw a free body diagram on the electron, it will feel this exact same attraction, whether this is a point or a sphere. But if it's a different geometry, if it is a triangle, it's going to be different, all right? So if this is a triangular, if it's like a pyramid charge like this, that is plus Q, it will have a slightly maybe bigger, or maybe I'm just going to make this up, right? But maybe a bigger force instead of an equal force like that, okay? So if you're talking about spherical charges, you might as well talk about point charge. So you'll start to hear this term point charge a lot. Okay. So now you know what that is. And what is the K? The K is Coulomb's constant. And it's actually a neat number. We'll give you this every time you need it in an exam, but it's identical to 9 times 10 to the power of 9. Okay, so it's actually a very nice number. Okay, so if you look at it in textbook, it'll tell you it's 8.99 or something like that. But yeah, 8.99 is good enough. We'll use 9 in most of our calculations. In fact, because it's 8.99, if you round to 2 significant figures or even 3 significant figures, it is 9.00. So 9 is actually okay most of the time, okay? Sometimes this was obviously discovered by Coulomb, but later on in more modern era, we realized where this law actually comes from. This law is no longer a fundamental law. It's just a historical law now. And sometimes the K in the textbook, you will see K is written as 1 over 4 pi epsilon naught. Right, so sure, so this is of course 9 times 10 to the power of 9, but this is the new constant. So we realize this constant, epsilon naught, it's called the permittivity of free space, is actually more fundamental than Coulomb's constant. So this permittivity of free space has something to do with how the structure of space works, and how easy is the electric force permittate the space, right? So it's actually more fundamental, and the Coulomb's law is get out of this. I do not remember this value off my heart. On top of my head, you can Google it. It's in your textbook as well. You can, and all these constants will be given if you need it. So Coulomb's law sometimes can be written in terms of that. So if people write it in a more modern way, I'm going to use slightly different symbols every time to get you used to not being attached to one certain symbol as well. And other than one more thing I need to tell you, that's all you need to know about Coulomb's law, and then we can move on to electric fields. So Coulomb's law is pretty simple. But before I go on to that, I want to point out another analogy with gravity. We're going to draw a lot of analogies with gravity in this section of the course, because both of them are non-contact force, and these are the only 2 non-contact force you know now. So that's why we always want to sort of draw that parallel. And if you remember, Newton's law tells you that anything that has mass will attract anything else that has mass by this law. Right? So this is the universal law of gravity, not just gravity on Earth, right? This is Newton's universal law of gravity, because anything have mass, right? So on Earth, of course, one of the object is the mass of the Earth, and then mass of whatever object you like, right? So the mass of the Earth would pull on the mass of whatever object you like, maybe your favorite apple or any favorite fruit. And you divide by the distance between the center of mass, not center of charge this time, the center of mass of these objects. So when you divide by that, it is the radius of the Earth plus a little height. But for a lot of the times, if you don't go up to the high atmosphere, as long as you're, even if you climb up to Mount Everest, it's like 4 kilometers. I don't know, it's probably something like that. But the radius of the Earth is 6,400 kilometers. So 6,400 plus 4 kilometers is nothing, right? It's the same. So we can pretty much put the radius of the Earth over here instead of radius of the Earth plus that little bit of height above the ground. That is pretty much a constant. As a result, I can rewrite this like this, right? And here's another exercise for you, it just should take you no more than 30 seconds, is plug in the numbers of ME and 6,400 kilometers. Google these values, right? You can Google G as well, 6 point something times 10 to the minus 11. You can Google that, plug that in, and you should find that that's equal to 9.81, right? So that's why everything on Earth is given by mg. It's basically a special case of universal law of gravitation. Now, I'm pointing this out because here is lowercase m, by the way. This is a capital case, but again, it doesn't matter. It's what they represent. It's not what symbol I use, okay? Here it represents two masses. Here I'm actually talking about the one mass is the Earth, one mass is your favorite fruit, okay? So you look at this, and these are very, very similar. So this is a key takeaway you want to see. It's a special case called inverse square laws. And these pop up a lot. Now, I know I probably have overused the term mysteries a lot in this course or this lecture already, but this is another mystery. This is another very big mystery, that why is the electric force so similar to the gravitational force? So this is the gravitational force on one mass to another. This is the electric force on one charge to another, right? So in this world, turns out things have charge and things have mass, right? Some things have zero charge, some things have zero mass. Light has zero mass, it doesn't really have any mass, right? But the difference is charge can be negative. Mass, as far as we know, believe me, and we've been trying to find it as physicists, as far as we know, there's no negative mass. So that's one difference. Despite that difference, why is it so similar? They behave almost exactly with some constant proportionality. In fact, a constant you shouldn't be worried about, because constant is just reflecting what units we're measuring things as. Turns out we choose SI units. So whatever we plug on this side, it better come out as Newton. And this is the constant that does that conversion, right? This is a constant that make whatever coulombs I plug over here better end up in a Newton on this side. So that is nothing physical. There's nothing deep about this constant. It's just the unit conversion. But it's proportional. The fact that it's the charge multiplied together and divided by distance squared, distance separation, distance squared, it's a very big mystery. And it's also only, amazingly, believe it or not, it's something we only understand in the past 40 years. We finally have a theory that actually understand this. And by the way, this was one of Einstein's last project. This is a mystery for hundreds of years since Newton have ever wrote down this and Coulomb wrote down this. And Einstein spent the rest of his life, even though he did sort of kickstart the quantum mechanics, he discovered relativity, he discovered E equals mc squared. He gave the first mathematical proof that atoms exist, all these amazing achievements. But in the end, he wants to really understand, can I unify these together? He's trying to find this unified field theory that combines these together. And it was, and he basically died before he found a solution. And it's around the 1970s when quantum field theory finally understand. It's a very new science in that sense that we finally have a theoretical understanding. Where does this come from? Where does this come from? It's a very big deal in theoretical physics. Okay, so that's all you basically need to know about Coulomb's law. But now I want to give you a little warning before, so the next half an hour is going to be on electric fields, which I don't want to jinx it, but let's see how I'm doing it. This is so far so good on time. What was I going to say? Sorry, I just lost my train of thought. So, all right, I'll see if I can get back to it in a second. Right, so if we're going to go to electric fields, oh yeah, I remember. It's about problem solving. because you're going to do a lot of homework. So the theory is it's that, right? So so you need to understand if I have two charges, then I know how to find the force between them. But that's basically just plug and chug. That's nothing challenging. What you will get in a lot of the homework is asked, what if I had three charges? Let's make it even more complicated, right? So let's say this guy has, so I'll give a quick example here. This guy has charge 2q. This guy has charge negative q, and this guy has charge 3q. And remember, when I ask for force, I need to ask for force on something by something. Okay, so let me ask for the charge on, let's call this charge number 1, charge number 2, charge number 3. Let's say I want to ask for the charge on 1 by, I want to ask for the force, the total force on 1. Right, let's say that's the question. What is it really asking? Well, it's really asking for the force on 1 by 2 plus the force on 1 by 3. Because remember, how do you do free body diagrams? You ask yourself what is touching it and what is not touching it. So you look at 1, what's touching it? Nothing. So we're going to make it very simple. In principle, we can make your life very difficult and actually add some contact force as well, right? Put it in water, now you have buoyancy as well, like that. If the leg starts showing up, there you go. So if you put in water, now you have a buoyant force as well. But let's keep it simple. So while we're studying electric force, let's forget about the contact force. Let's just focus on it. So there's nothing contacting this little guy. The only forces acting on it is non-contact forces. So what are the non-contact force we just learned is there's two types, right? Gravity and electric. So here, clearly, if things are charged, we talked about when things are charged, as long as they're not neutral, then they have an electric force. Now, do we care about gravity as well? And hope this is where slide number 2 comes in when I talked about how strong electric force is. Gravity in this picture is completely negligible. If you do include it, unless you have a huge black hole right next to it, if this is just placed on Mars or placed on Earth or in any reasonable planet, that gravitational force is going to be 10 to the 40 times, roughly 10 to the, it might be 10 to the minus, it might be 10 to the 39, it might be 10 to the 41. Don't hold me against that 40, but roughly speaking, it's 10 to the 40 smaller. So are you going to care about the 40th decimal place? No, right? So that's why the only non-contact forces are the electric force. So that's why we only add these two, right? You understand? So now what we will draw, we'll change our pen to orange and we'll draw the free body diagram here. Let me change number 3 to negative, actually, in order to demonstrate my point. So how would you solve this? So force on 1 by 2, we'll look at them one by one. We'll first look at this guy, right? This is attractive because it's the one is positive, one is negative. Okay, so you're going to draw that arrow there. Since everything is on 1, let's just label what is the force due to, and I don't need to label F1, 2, right? Sometimes I get confused. Is this on 1 by 2 or by 1 on 2? I never know when textbook write this. So if you see what I do, I always write subscripts. And hopefully halfway through the course, you understand, you have start to get used to my way of thinking is I'm not afraid of labels. The more label, the better. It makes it clear. F1, 2, God knows what that means, right? But here, everything is on 1 since I'm starting from 1. So I think this is obvious. But I try to avoid things like F1, 2 if I can help it. And then now that is F2, how about F3? So this time it repels. Okay, so this is F3. So now you add these, but they are in different directions, right? So now you need to add them vectorially. There's 2 ways to do this. So one way is, let me recopy this out. So that's F2, that's F3. One way is do it in terms of a picture. So let's call it geometrically. So when you do that, right? So what do? You need to add them head to tail. So first you need to move this to this side. You need to move F3 over here. And then or you move F2 on here, it doesn't matter. Either way you see, you end up at the same point. So you add them head to tail, and then you go from the beginning to the end. This is the F net or F total. I'm gonna use these words synonymously as well. the total or F net, because total, I mean, not just adding the magnitudes, I mean, adding the vectors, right? So what is the, let's say this one is some angle here, and this one is horizontal along the x-axis. So what is the new angle? And what is the new angle? It's called phi. And what is the new magnitude? So you're interested in the new angle and then the new magnitude. Now, if I don't draw the vector sign on top, it means magnitude, okay? So when I just write this, this is just a lazy way of doing this. So either have the magnitude signs and the vector sign, or none of both. They mean the same thing, okay? Equals question mark. So magnitude and direction, you can do that. So here you need to, if you do it this way, then you need to be good at trigonometry. So you find out, okay, so this one subtract by this, you maybe use the law of sines and law of cosines to figure out this. So this is one way of doing it. Okay. Any vector problems can be done in two ways. The other way is algebraically. It's a little bit more algebra, but it's more straightforward. So a lot of professors would force you to do this, and you might wonder why not to do this. It's really for your own good. By the way, if anyone is good at, if you're comfortable with trigonometry, this is a very legitimate way of doing it. And personally, I actually don't see which one. Sometimes this is easier, sometimes this is easier. But for teaching purpose, this is easier. And how you do it algebraically is what you need to remember in 3A. So this one lies along, first you need to introduce, number one, you introduce an axis. And then number two, you resolve your vectors. So what does resolve vectors mean is you take something that is not on an axis, take any non-axial forces on axial vectors, so vectors that doesn't lie on an axis, and split it into its components. So you take this guy and split it into the x and y component like this. So if this is F3, it becomes to F3x, F3y. This is F2. Incidentally, F2 is lying on an axis, so F2 is just F2x, right? There's no F2y component. And now you just add up all the x's together. So the net x is, let's call this positive, right? This positive direction, x is F3x minus the length. So the length of this minus the length of this, right? So you see, I don't have that vector sign over here. So you either write this or you write F3x plus F2x, okay? I suggest the former. I suggest you first deal with the directions on the diagram. So always draw a diagram. Deal with the directions first. And then, so now you know which one minus which one. And then now deal with the actual calculation and plug in the numbers. Instead of doing it like a vector where you deal with the magnitude and the direction in the same step, okay? This is doable. If you're good at vectors, by all means, this is easier in my recommendation. And then now you do F net y, right? So F net y is just F3y. So whatever number that is, you resolve these forces with sine cosines like that. And now you have the x component, you have the y component, and then you know the total magnitude is given by the Pythagoras theorem of net x squared plus f net y squared square root, like that. Okay, so in this course, you will see that understanding the concepts and doing the math is a completely different thing, okay? So I will move on with my lecture to introduce the next concept of electric fields. And in discussion session, you will go and you will do some of these exercises that will help you with your homework. Of course, you can start your reading and you can go ahead and start them as well. Okay. So now let's go to electric fields. What are they, right? So remember another litmus test of when you learn anything new, ask yourself, can you explain that concept to an 8-year-old or a 5-year-old, okay? So let me start with an opening question and see what you think. So if I have two charges, I have a very big charge and a very small charge. So one is very huge charge, let's say 10 coulombs, and the other is 0.01 coulomb, like this. All right, so if we draw a free body diagram on this guy, obviously we will see it will get repelled, right? So this is the force on, let's call it A and B. The big one's A, the small one's B. So the small one will experience, right, we have a force on B by A, and the big one will experience another force, right? This time it's the force on A by, right, B. This one is on A by B. Now in the chat, can you tell me intuitively which one is a larger force? Is the force on B larger due to A, or is the force on A larger when it's due to B? Okay, put in either which one is larger, on B, put in on B or on A in the chat, either on B or on A. All right, good. So this is one thing. If you like to trick people, it's one of those great trick questions. Intuitively, I completely resonate with you. No matter how you look at this, it looks like the force on B is the same. But now you look at the subscripts carefully, and now with your understanding of physics, you might want to try again. Right? Remember, this is on A by B and on B by A. Does anyone want to change your answer? Exactly. So it is the same because of Newton's third law, right? If you switch the subject and the object, right, then you have the same magnitude. I'm probably being a little bit misleading over here intentionally. I should have drawn them with the same length of the arrow. So let me fix that to mislead you. But they will be the same. The reason is, now let's look at the law and see what it tells us, right? Because now you plug this in and you put in, right, QA, QB, the magnitude of this is QA, QB over R square, right, the distance between them. And then this guy, you plug it in, is K, QB, QA over R square. Of course, they're the same. The magnitude, and now you see why Coulomb law only gives you the magnitude, right? Is the same, it's equal, but the direction is governed by my fundamental rule in one of my early slides. If you look back, I say there's two rules. One rule is that negative charges, like charges repel. So you use those rules to tell yourself basically those rules is what I call common sense. If you know common sense, you can tell the direction. And then common sense won't tell you this, but if you learn this formula, right, the formula will tell you the magnitude. Common sense will tell you the direction. So that's how you should do these problems. Now, this leads us to the question. This seems very confusing. I mean, yes, I understand the theory now, but it's not very intuitive. Why? Because if I want to know which guy is stronger, which guy has a bigger electrical influence, clearly A is more influential electrically than B, right? But force is quite a crappy unit, quite a crappy quantity if I want to just tell that, because no matter what I put here, the force on A and by B is the same. Then I couldn't, if I just look at the force, if I calculate the force on A by B and then I calculate the magnitude of force on B by A, I have no clue which one is larger or which one is, electrically more important. Here comes in the idea of electric fields. By the way, this is the same thing as if you want to ask someone else the force on the Earth to the moon, right? The moon would, the Earth would pull the moon over here, the moon would pull the Earth over here, pull on the tides, all those things. Which force is larger? It's the same theory. They are the same. It looks like the force on the Earth, the force on the moon by the Earth is stronger, but it's not. This is, again, equal and opposite. Okay, so yeah. Now, okay, so here comes the idea of electric fields. So let me give you the definition, okay? So the definition is force per unit charge. But force per unit charge exerted on a positive test charge. This is very long, but this is a definition you will need to commit to memory. Let me break it down and make it easy, because the first part, the key part to get your points for defining this is force per unit charge. If you can do that, that is the main point. The fine print is here. If you don't write that, probably you won't really even get marked off. But it is good. It is useful. It is very crucial in understanding it well. Okay, I'll dissect each of them a little bit more. I'll tell you the symbol first. The symbol we use for electric field is E. But remember, we'll actually have 3 different quantities later on. We have the electric field strength. Hi, sorry. Hi, sorry, I apologize. Let's hope this goes back. Okay, so there's 3 concepts: electric field strength, electric field lines, and electric field vector. Okay, we'll get to those in a very short moment. All right, so let's break this down. Force per unit charge. Let's write the equation form is electric field, which is given by E, is force per unit charge. So F divided by Q. All right, so that's the basic, but now let's look at the fine print. It's the force exerted what? Because it's always on something by something, right? So it's on a positive test charge. So what we divide is divide by a test charge over here. Okay. So now with this, to understand this, the best way to understand this is with an example, with the previous example. So let's say this is big Q, this is small q. So let's calculate the force on this guy. Let's calculate the force on this guy. Right? The force on this guy is KQQ over R squared. But if I want to find the electric field of this guy, if I want to find the field, the force on this guy, the field of this guy, then I need to take the force, which is KQQ over R squared, divide by something that I need to use to test this guy. And that's this one. So I'm using this, treating this as a test charge. It has to be positive. And then we use this to test how strong this is. So, right, so now I can calculate the force. Okay, so let's say it repels, right? So I calculate precisely this force, but then I take this force and then I divide by this guy. Okay, now the answer I get is this. Okay, so I'm going to introduce the jargon test charge and source charge. So if I want to find how strong my source is, so this is the source now. I don't actually want to calculate the force. I actually want to calculate the field of my source. Look at my result after I apply the definition of electric field. I get a function that is purely in terms of how strong this is. Nothing to do with this. Because what was preventing us to compare which one is stronger before was this annoying little q. Because now if I calculate the other way around, right? If I, let's call this Q test, right? But now I have a small charge. I can find another Q test, right? And I can find the electric field of this guy. Let's see if it's smaller or not. So we apply the definition. First of all, it's force per unit charge, test charge, force per unit positive test charge. So what is the force on this guy? On Q. So it's KQ, Q test, divided by R squared over Q test This cancels out, so I get KQ over R squared. So this is the electric field of this guy, and this is the electric field of this guy. So look, which one is stronger? Clearly, the electric field of big Q is larger than the electric field of small q, right? Because I've divided away an object to use to test it. So this is the idea of electric field. Let me try to summarize this. The idea is, the goal is, if you try to explain this to a 5-year-old, you say, I want to know how strong electrically is my source. Some guy, I want to know how electrically strong or influential is this. So how do I do that? That is this quantity, electric field, that's the quantity that tells me that. It tells me how strong this guy is. Right? Now, practically, how do I do that? I find a test charge. I find something. This can be 1 coulomb. This can be 0.1 coulomb. It doesn't matter. Usually, it's a small thing to test. Usually smaller than the other. And then you calculate the force. So that's step number 1. Step number 2, you divide away the test charge, because precisely you do not care about the test charge. You care about your source. That's what you want to find out how strong it is. So you use something to test it because that's the only way you can find the force, but now you divide away, okay? So hopefully I repeated basically the same idea in 3 different ways and saying it in slightly different words. Hopefully that makes sense. All right, so I'll say one last time. You try to understand, your goal is to find out how strong this guy is, right? So you find something to test it. So you put a charge here, find the force that is between them, right? So you find out what is the force exerting on this guy, and then you divide away whatever you use to test it, okay? Now it's very abstract with electricity, but it's very obvious with gravity. So I'll use the analogy with gravitational field. You can define the same thing called gravitational field. Let's call it I. Don't ask me why I, because G is taken. Is the force of gravity divided by a test mass, okay? So if I have the Earth over here, if I want to find out, if my question is how strong the Earth is gravitationally, so you go like, oh, let me find a little weight over here to see what is the force on the weight. What's the force on the weight by the Earth? But this is not fair, because if I just want to know, notice this is my question. If I want to know how strong the Earth is, now I just calculate this, it would depend on my mass of the weight as well. It would depend on my test mass as well, right? Because this force is Gm of Earth, m of whatever my test mass is. This is now a test mass, divided by R squared, right? It is not a fair comparison if I just look at the force, because it depends on the test mass over here. The only way to be fair to calculate how strong the Earth is, I do not care my test mass, because if someone else uses a bigger test mass that is 10 kilograms, you will get a larger force, but that doesn't mean that the Earth is stronger. It just means that your test mass is stronger. The way to get around this is not calculate the force, but introduce a new idea called field. And the new idea is you divide by whatever object you're testing it with. Then I can calculate the field, okay? So incidentally, if you push this through, right, you divide this, you'll find that the gravitational field of the Earth is Gm Earth divided by R squared, which is precisely what we called, so you take that and divide by test mass, sorry. This is precisely what we called earlier G. So this G, acceleration due to gravity, is also called the gravitational field sometimes, okay? Right, so summarize over here, the gravitational field is force of gravity divided by a test mass. An electric field is the force of the electric force divided by a test charge. Okay, This is probably the most abstract part of today's lecture. This is electric field, the concept of field, and this is gravitational field. You can use big G or small g, or I is another common one. It doesn't matter. Okay. Okay. So this is the definition. Commit it to memory. I'll write it one more time because it's so important to understand this, to memorize this definition. It's force per unit charge. And you can figure out what the SI units is, which is newtons per coulomb. It doesn't take a genius to figure that out. Okay, all right. So now I will clarify the difference between the few terms of electric field vector that I motivated. They are all different: electric field strength and electric field lines. Okay, so if you look at the definition here, technically speaking, the force is a vector, which means the field is actually a vector as well, okay? But as I told you a lot of times, it's easier to just look at magnitude and direction separately, okay? So electric field vector is this. This is the most formal definition, but I'm going to write this down, but most of the time in practice, when you're doing your problems, you don't need to use this directly. I would say 80% or 90% of the time, you don't have to. Maybe there's one or two problems. We'll introduce it to you to get you to learn it once, but we won't. The focus is not heavily on this formal vector way of doing things. Okay, the easier way is look at magnitude and direction separately, and electric field strength refers to the magnitude. Okay, so when we write E, this is a lazy way of writing this. Okay, a small pet peeve of mine is when people start writing things like this, either this or when it's not balanced, when they have something like this. You see why this, first of all, you see why this is ugly, because you have a scalar on one side and you have a vector on the other side. Mathematically, this is not well defined. It cannot be. This is just some in between that I'm not sure what do you mean, because writing the two sides is redundant if you just mean the field strength. And if you're lazy, don't write these as well. If you're not lazy, you should also write a vector on top. So it's either or. There's not a big problem with this. It's just a little bit weird to me. This is mathematically wrong. Okay. So what does this mean? Well, yeah, so that's just the magnitude of whatever you're calculating, right? So so essentially this is the magnitude of this. Okay, electric field lines, I should explain. Electric field lines basically tell you the direction. So if the field strength tells you the magnitude, the field lines tell you the direction. Okay, so this is lines that traces the motion of a positive test charge. I'll put it in simple words. That traces how a positive test charge moves. This is what electric field lines is, right? And I think it's best explained in examples. So if I have a positive charge like this, how would a positive test charge move? So if this is my source, so remember the difference between source charge and test charge. Okay, so if this is my source, if I put a small positive test charge here, it will go this way, right? If I put a small charge here to test what's going to happen, that's why it's called a test charge, it will go this way. If I put another charge here, it will go this way because it will get repelled like this. So now I can change my colors of my pen and just sort of draw out these lines like this. And I can just draw out a lot of lines radiating from it. And these lines, if I put an arrow next to it, it will basically, these are called electric field lines. So it represents the electric field. It represents the direction of the electric field. So these are electric field lines, what they do is they represent the direction of the electric field vector, if you want. And to draw them, you basically ask yourself, how will a positive test charge move? And then you draw the line that traces it out, okay? So just to redraw this. So for a positive charge, let me redraw it in a more pretty way. This is how the electric field lines look. So you might get questions on draw the electric field lines of the following electric sources, okay. Spoiler alert, this is probably, these are good short answer questions to just sketch these diagrams, right? So how does the negative charge would look? I'll just draw the answer first and then we'll explain it. It should be quite intuitive after I give you the answer, is this. Again, how do I know? Because the electric field lines is lines that trace how positive test charges move. So you put a tiny, minute positive test charge here because you don't really care about it. You don't want it to be influenced by its mass or its own inertia. You just want to see what is the influence on this guy. So you put it here and it'll get sucked in. It'll get sucked in, right? So wherever you put a positive test charge, these lines represent how a positive test charge moves. Does that make sense? Okay, good. Now, how about if I have a positive charge and a negative charge together? So I have two sources like this. How do you draw this? Again, the trick is, if you know how a positive charge move, you know the field lines around, so these are the field lines around the positive test charge is, you first draw it near here and you draw it near here and try to connect the dots, to connect the lines, right? So one of them is radiating radially outwards. I'll introduce another jargon. It's called radially outwards or inwards. Radially just means symmetrically going away from each other. Okay, I'm not going to write it out to save some time. So you first draw the field lines next to the charge, right? Put in the little arrows. And then now you join the lines together, right? So you'll get one big line here. You might get another one here, get another one here, right? You might have seen this rough diagram like this before, almost like a butterfly, right? What that does is, again, it tells you, let me zoom in, if you put a positive test charge somewhere like this, if you put it over here, it will basically follow these lines. And at first it will get, if I put it very close to the positive side, the green test charge would start repel. But as soon as it leaves here, now it feels the influence of the negative charge and will start to get pulled over here, right? And then it will get pulled in on this side. So that's why, that's how we know what these lines represent, or that's how you draw them, okay? But more importantly, what are they useful for? If you need to ask that question, is they're useful for telling you how do positive charges flow under the influence of these sources, okay? So this time I have two sources. Okay. Oh, I'm almost time. Just to give you an idea, I'll wrap up the main content in 5 minutes and pretty close. Good. The network delay threw me off a little as well. Okay, so if I have two lines like this, sorry, two planes, actually, yeah, this is actually a plane, but I can just draw the cross section. So a positive plate and a negative plate of charge, how would the line move? How would the field line look? Okay, let me just draw the cross section for simplicity. Well, imagine putting a positive charge here. What will it do? It will get repelled on this side and attract to this side. And exactly, you're right. Okay? So it's a very simple field lines like this. Okay? In fact, on the side, you might get it to repel a little bit higher and around, you know, on the bottom like this as well. So if you want to make it even more realistic, right, there's these side as well. The lines on the side, or the curvy lines on the edge, these are called edge effects. And when we're talking about parallel plates, a lot of times we don't care about them too much. We're more interested in the very uniform part in the middle. And if you make the plates very, very large, you can't really see the edge effects if you're a small ant living in the middle over here. Okay, so these are a couple of examples, and I'll give you an exercise. You can try some of these at home. What if you have a big charge and a small charge? Okay, how would it look? Can you draw the field lines for this? And what if you have a positive charge here and you have a negative plate like this? How would the field lines look? What if you have a rod? If you have a rod of positive charge, how would the field lines look around the rod? And maybe finally, if you have a triangular charge, how would the field lines look around it? Okay. Maybe for the rod, do one for a positive rod, and maybe do one for a negative rod as well. Okay. Introducing a few jargons. A rod like this is called a line charge because of obvious reasons. A plate like this, it's called a surface charge, or what's the word? Plane charge, yes. Okay. And if you have single points like this, these are point charge. So in some sense, I'm just introducing some jargons. If this is 0 dimension, if it's 1 dimension, if it's 2 dimensions like this. And if you have something like a pyramid, we don't have a special name for it. Yeah. Okay, so this is the end of the main part of today. There's a few other things we'll talk about tomorrow on. Okay, so now that we know the basic, you've understand basically what is it for. Just a quick summary is, I'll save time by not writing things out. Just showing you the slides from before. I won't write things out, so maybe you want to put some stars next to your notes. First thing, learn this definition. Okay, this is the main part, and this is the fine print. Okay, if you get this part in the exam, you'll get the points, force per unit charge. But for what we're going to do tomorrow, it is really beneficial that you also recite this part as well, because it tells you what it is. It's the force per unit charge exerted on a positive test charge. Okay. One small comment that it's not a big deal. I actually applied it slightly wrong over here. If I follow my definition properly, I should look at the force per unit charge, right? So you see the field is force per unit charge, per unit test charge exerted on the positive test charge, but I've drawn the force exerted on the source, not the test. So this is a small correction that if I have time, I would erase it and make it pretty. But I should have drawn it here. But you know that I said it's a small correction. It's not a big deal because the force is equal. The magnitude of the force is equal. I'm just caring about the magnitude. Okay, so it doesn't matter which one I draw on. Technically, I should draw the force on the test charge. In fact, for the gravity one, I drew it right. So for the gravitational field, is the force per unit mass on whatever test mass. So you see, I have something to test how strong the gravity is. So I calculate the force on the test mass and divide by the test mass. So that's the definition of what fields are, okay? So that's number one, you need to know the word definition. Number two, you need to know the equation definition. And then number three, you need to know what electric field lines, how to draw them, because next, basically, just to give you a teaser, next we are going to not even worry about drawing the source. I'm just going to draw you the lines like this to give you an idea. I am just going to tell you, these are the electric field lines, and I'm going to give you a little positive charge and put it over here and ask you, which way will it go? All right, you'll go like, yeah, from today, I immediately know that it'll go this way, right? And then it'll move here. And then when it's here, it'll move here. When it's here, it'll just move along my lines. All right, that's a simple thing. But now my question is, how fast does it move? So now you need to do the calculation, right? It's very simple. We'll give more examples next time, but if you know the definition of this, then you'll see that what is the force exerted on this guy? Well, you just rearrange it. Right? So if I give you this, if I just give you, I don't need to give you any source, right? I just give you the field, and you know what is the charge over here, and then you'll know the force. And remember, the force will tell you its acceleration. And then once you know the acceleration, you can calculate its velocity. So that is where the chain of logic goes, right? So and so that's one thing we'll talk about tomorrow. Another thing is a variation on this is, now, okay, this is a simple question, the blue one. If I put a blue charge here, it will go this way. But what if I put an electron over here that is of negative charge? Which way will it go, right? So the simple answer is also, it's nothing deep. It's just a negative charge will do whatever a positive charge do in the opposite direction. It will behave exactly the same as a positive charge, but in a different way, in the opposite way. So if the positive charge follows the electric field lines, the negative charge will, you guessed it, it goes against the electric field line. So the negative charge will go this way if the positive charge follows the electric field lines, right? And we'll see why this is useful. Why do we care about this in the next lecture? That way. Okay. So I think I've finished the main content over here. So thank you very much. I said in the beginning that there's an extra part, an interesting extra thing that I should talk about. So let me also supplement this and include that in the recording as well. It won't take more than 3 minutes, okay? All right, so here it goes. It's about fundamental forces, and I'm not gonna write too much things down. I'm just gonna talk about it. And non-contact force. So, okay, I'm just gonna talk to you. Now this chapter we introduced a new non-contact force, right? Then then I told you there's only 4 fundamental forces in the world, in the whole universe. So if I have the 4, I can explain everything. Now you should be very confused, because in the beginning of this course, or at the whole point of 3A, you learn that there is a whole long list of force. There is friction, there is tension, there is normal force, there's buoyant force, right? Our whole career up to now is just compiling this list of forces. And then now I seemingly made a contradictory statement that there's only 4. What's going on over here? I'll summarize this in 2 minutes. What's going on is, here's the profound statement. Every single force in that list is a special case of the 4 forces that I mentioned, believe it or not. In fact, 99% of that list is electric force. Okay, this is so profound I should write this down, but I'm just gonna make it efficient and I'm just gonna talk to you. 99, you might want to write this down yourself, 99% of that list is electric force. Just in 1 minute, I'll give you a few examples, is, let's say, normal force. And I've actually given you that example, is if you put a book on a table, what is the force holding that book so that the book does not fall through the table? is the repulsion between electrons and electrons. It's the repulsion between the electron of the book and the electron of the table. That is what we called normal force in the past. But now you realize that normal force is actually an electric force. That's why we care about electric force. Now, what are other contact forces? What if I just push, I just push you on one direction? I want you to get away from me, so I will exert a push to the right. What's going on is the electrons on my hand, it's the exact same story. It's repelling on your body as soon as I push on you, right? So you see, that is actually electric force. So I can't really think of any contact force that is not electric force. And as a result, the profound statement number 1B is, in this world, there is no contact force. Every single force is a non-contact force. You look at the book and the table close enough, if you zoom in close enough, they're not touching. They're repelling with a tiny, tiny bit. There's a gap over there. It's the electric force that is repelling. You look at your feet on the ground right now, your butt on the chair right now. It's not actually touching. There is I mean, yes, it's going to create a dent in the fabric, but that's because the electric force is pushing the fabric, bending it down. There's no contact force. Is a myth. Now, why do we talk about contact forces in 3A? Is because in the macroscopic world, in the daily life, if you don't zoom that close, then you don't really care. We just make it easier for ourselves to talk about contact and non-contact force. So this is the statement, right? So in summary, the idea is there is no such thing as contact force. Everything is non-contact force, and every non-contact force, the majority is made out of electric forces. There's a few examples that it's not, and those are the other three. In the world, there is only non-contact fundamental force, and that explains the term fundamental. Okay, all right. Thank you very much. Hope you've enjoyed this. I will look at a few questions here, but that's the end. Thank you very much. Have a good night. Okay, Professor, I have trouble with my Zoom connection. Well, so do I. It keeps lagging. I think it's my end, because I think that is true for everyone, right? If you guys, you're welcome, guys. See you. I think, yeah, I think it's on my end. My guess is maybe a disadvantage is when we're in the evening. I think more people are using the network. So I think that's what's causing it. What I did already today is I have restarted my computer before I start the Zoom. I did not do that last time, but I do it most of the times just to ensure a stable connection. But it still seems to lag. So we'll see if it gets better, if it's a once-off thing or not. Yeah. Oh, it happens for discussion as well? Oh, okay. Maybe it's really just a lot of people using this network, I think. Happened for discussion, yeah. I see, right. Another question from So Park is, on the schedule, the mock final is mentioned. If we do better on it, does this replace our final grade? I was confused of the wording. Yeah, let me talk about that more at the end. For now, let's focus on this first, okay? Maybe the heat, oh yeah, maybe it's the heat wave. Maybe it's the power that is less stable. Yeah, maybe, yeah. Cool, any other questions? Yeah. Okay. All right, good. I hope things will become smoother and so on. Thank you guys for staying. And if it weren't for the network connection, or those lagging, sometimes I look up at the screen and I already see that it's a little bit slow and it's lagging. So I'm halfway through, I'm waiting for that to show up before I have to say the thing. I think if that's not, I'm actually getting better on the time, but that's screwing up my pacing a little bit. All right, enough of my excuses. But all right, good. See you guys tomorrow. Bye.